Hello, 171 class. This is your notes for 3.5, the third part. And here we're going to talk about logistic growth and the logistic growth model. So the logistic growth model, what it does is basically it compensates for the fact that exponential growth cannot realistically, in most cases, continue for a long period of time. It can't sustain that growth. If something's growing exponentially, it starts bending upward. If it were to keep growing exponentially and keep bending upward and keep bending upward, the growth would eventually get to a point where the graph is almost vertical. And as time goes on, now we're getting like almost infinite growth. And it's just not realistic for that to happen at some point. So what logistic growth does is it takes into account that a exponential growth can only be sustained for so long, and at some point whatever is growing exponentially is going to run out of steam, or it's going to run out of resources. If it's like a population, there's going to be too many people or too many bacteria in an area, and that rate of growth can't be sustained, and then things will eventually level off. And what we end up with is this horizontal asymptote that is like an upper limit, that something cannot grow beyond this number at all. I mean, it's impossible. So anyway, what we end up with is a ceiling, and that's what this value C is. It's the limiting factor of the growth rate. You can't grow beyond this value. It actually can't even attain that value. You can get close, it just can't get there. So that's what the C is. Notice the E down here is the natural base. It's not a variable. The A is a variable. Okay, it's a constant. The B is also a constant. So the only variable here is time. C is a set number, A is a set number, B is a set number. E is the natural base. T and F of T, or a lot of times we use A for these growth models. A meaning amount, T meaning time. Those are typically the only variables that you see in these, and the rest are specific parameters, or again the natural base there. All right, C and B are both positive constants. A doesn't necessarily have to be, but C and B do. Okay. And again, C is that growth factor. Now, the reason why C is called the ceiling here is because of this piece that we're adding to 1. Right? As T gets bigger, as time goes on, and T is getting bigger and bigger and bigger, because B is a positive number and T is positive because it's moving to the right, original amount T is 0, so we're moving to the positive direction. So B and T are both positive, and positive times positive is positive. But then because we have that negative out there, what we end up doing is raising E to a negative number. And the bigger and bigger and bigger T gets, the smaller and smaller and smaller E to that negative power gets. Like for instance, E to the negative 1 is that number. Okay, E to the negative 10 is that. Okay, now we're already in scientific notation. 4 leading zeros. All right, E to the negative 100 is teeny tiny. All right, 43 leading zeros, virtually 0. So this part right here, E to the negative BT, is approaching 0. And then we're multiplying that by A, multiplying something that's getting close to 0 by A, which is just some number. Well, any number times something that's getting close to 0 is also going to get close to 0. So eventually what happens, the further and further we go out to T, eventually this piece right here goes away and becomes 0. And then what does this become? Just C over 1 plus 0, which is 1. C divided by 1 is C. So that's what happens. As time goes on, this function just becomes F of T equals C, which is a horizontal line passing through C on the y-axis. So anyway, that's why this thing looks the way it does, because as T gets bigger and bigger and bigger, this part goes away. Alright, but what you need to know about logistic growth is it's a realistic exponential model. Right? We can grow exponentially for a short amount of time, but then eventually we have to level off, or in some cases even decrease. But we can't sustain growth forever. We have to eventually level off. Most things, anyway. Alright, so here's a logistic growth formula. So this number describes the number of people who became ill with some influenza T weeks after its initial outbreak. So this is how many weeks later. Right? How many people became ill with the flu when the epidemic began? So when T equals 0. So when T equals 0, I just plug in a 0 where that T is in the formula. Well, it's negative 0. It's fine. I put negative 0 in there. You wouldn't have to. But I just get 100,000 divided by 1 plus 5,000 e to the 0. E to the 0 is 1, so this ends up being just 100,000 divided by 1 plus 5,000, which is 5,001, and we get that number. So when T equals 0, we end up with roughly 20 people that were sick. Alright, how many people were ill by the end of the 4th week? Alright, T is the number of weeks after, so we just replace that 0 with a 4. Alright, that's another reason I left negative 0, because I'm going to go back and plug numbers in. So about 1,080 were sick 4 weeks later. Alright, what's the limiting size of the population that becomes ill? The numerator, the 100,000. So we can't have more than 100,000 people. If I plug that function into y1, I can then go to the table, second graph. If I look at this as I make time get bigger, the values get bigger, I can see these numbers over here to the right are getting closer and closer and closer to 100,000. Eventually it's so close that it just rounds to 100,000. The calculator just rounds it. It's actually not 100,000, it's just rounding it. And eventually there'll be so many nines here that it'll even say 100,000 over here on the right hand side. But just know that you can use the table to kind of get that limiting factor. So there, see there, it just runs out of decimal place and just displays 100,000. It never really gets there. The calculator will make it look like it gets there, but it actually just has so many nines after the decimal point that it just rounds it to 100,000. But you can always get that. If you have a logistic growth model with that e to the negative power in the denominator like that, you can always get the limiting size from the numerator. Alright, Newton's law of cooling, another exponential type function. It's just the formula looks a little bit different than the logistic growth that we were looking at before, or the exponential growth that we were looking at before. So it's still exponential. That's why it's in this section. Alright, so what this is temperature of something heated at any given time. C is the room temperature, or wherever the object that had been heated is exposed to. So there's the temperature of the room. And then T0 is the initial temperature of the heated object. So it comes out of the oven, and it's in this room with the temperature C. T0 is the temperature when it comes out of the oven. T is how much time has gone by. And K is some negative number. That's the cooling factor of the object. So again, because this is negative, time is positive, we're moving forward. We end up raising e to a negative power again. So once again, as time goes on, this approaches 0. So all of this is going to approach 0 eventually as time gets bigger. And then the temperature of the object that came out of the oven will eventually be room temperature, or very close to it. Because of that fact that, again, K is a negative number. Alright, so let's look at this and see how we can do with this. Pizza is removed from the oven, has a temperature of 450 degrees. So that's our T0 right there. It is left sitting in a room that has a temperature of 70 degrees. That's our value for C. After 5 minutes, there's our value for T. The temperature of the pizza is 300 degrees Fahrenheit. Alright, use Newton's law of cooling to find the model. So the temperature is 300 degrees Fahrenheit after 5 minutes. So 370 plus parentheses T naught is 450 minus 70, and then e to the k, and we're solving for k using this t 5 minutes right now. So we're going to flip-flop this, the k and the 5 again, because I put it in the formula that way, but anytime that the variable is first, I switch the two numbers around. Alright, and now this is just like any other problem exponential equation where we're solving for this k. We're going to move all this stuff over to the other side, divide, and then bring in natural logs. So subtract 70 from both sides. I got a 230 equals 450 minus 70 is 380 e to the 5k. Alright, divide both sides by the 380 to get the exponential part isolated. Alright, so those zeros will cancel. So I got 23 over 38 equals e to the 5k. Now, just like in the previous problem we've done, you're going to bring in the natural logs. I'm going to leave the 23 over 38 as a fraction because I don't want to round until I have to round. Right, e to the 5k, natural logs cancel. So this is natural log of 23 over 380 equals 5k. Alright, and then I'm going to divide both sides by 5. So the natural log of 23 over 38 divided by 5 equals k. Alright, and then I can make that approximate. Alright, type in the calculator, enter negative 0.1004. So k is about negative 0.1004. Alright, so the model would then be t equals c is 70 plus parentheses 450 minus 70, which again, then I'll do e to the negative 0.1004 t. But again, I would write 450 minus 70. I would write that as 450 minus 70 is 380. So there's our model that we could use to answer the other questions. Alright, and then what's the temperature of the pizza after 20 minutes? Well, now we just use our model. We plug in everything from the model into our calculator and just replace t with 20 for the 20 minutes. And there's 121 degrees. Alright, roughly. Okay. When will the temperature of the pizza be? 140 degrees Fahrenheit. Now we have to take the t here, replace it with 140, and then go through and solve for that t. Alright, and now I'll plug that in, and now I'm just going to solve for the t. So subtract the 70 over. Again, all the work for these is virtually the same for these exponential equations. Divide both sides by the 380. I always wipe out the zeros if they both end in 0. So 7/38 equals e to the negative 0.1004 t. Natural logs of both sides. Right, the natural log and the e wipe each other out. Right, and then divide both sides by the number in front of the t, and that gives us our approximate time. Okay, so then plug it into your calculator, you get an approximation. Alright, so I get 16.85 roughly. 16.85 minutes for it to get down to 140 degrees. Alright, so that is Newton's law of heating and cooling and the different types of questions you can be asked. If you're asked to find out how long it takes to get to a certain temperature, you're going to have to do this process used to find k again, but now just use it to find t. And that's the temperature questions are easy, just plugging into the formula, but the time questions and the find the value for k questions or find the model are where you're going to have to use the techniques from this chapter to be able to do the work.